Well, hi there, sports fans, and welcome to another exciting edition of Physics 12. And today we're looking at lesson 3.4, which is on energy conservation. And this goes back to the idea that energy cannot be created nor destroyed. At least we can't create nor destroy energy. God is the only one that can do that, obviously, but we can't. So we need to account for all the energies of a system when energies are transformed. In other words, they change form within a system. So we need to be able to account for all of them, and that's what today's lesson is all about. So we're looking at mechanical energy and its conservation. And so if there are no non-conservative forces, so non-conservative forces like friction or applied force, that kind of thing, the sum of the changes in the kinetic energy and the potential energy is zero. So in other words, there is the total energy of a system is maintained, and the kinetic and potential energy changes are equal but opposite in sign. So if you have a change in kinetic to potential, or from potential to kinetic energy, that means whatever amount of energy is changed, that will show up in the other form. So if you lose some from potential to kinetic, then that change will be accounted for. So the net change is actually zero, and so if you take away some potential energy, then you add to the kinetic energy of the system, and vice versa. So this allows us to define the total mechanical energy as such. So the energy in a system is the kinetic energy plus the potential energy. And its conservation, which we sometimes write like this. I will show you another way to write that a little bit later on. But the energy final, or at a different time, compared with the energy initial of a system, that has to be constant. So we have to account for all the different energies that are at play in a particular system when energies are transformed from one type to another. So problem solving, how do we do that? Well, let's look at an example here. Let's say you have a person here standing holding an object a certain distance above the ground. So in the image on the left, the total mechanical energy is given by this, where the energy is the kinetic energy plus potential energy equals 1/2 mv squared plus mgy or mgh. Oftentimes we use the h more often, actually. And so the energy buckets, which will appear in just a second on the right, they show the energy. They show how the energy moves from all potential energy. So initially we're starting with all potential energy, and then eventually when it gets down to the bottom, it will be all kinetic energy. So let's see how that works. So initially, before the object is dropped, it's being held in place by this person. So the velocity is zero. There is no kinetic energy. It's all potential energy, which is given by mgh. And so you can see in the energy bucket here, it's all potential energy at time zero, or initially. And then at some time later, when the object is dropped, and so now it's just 1 meter above the ground, then we have kinetic energy and potential energy. So at this point here, you can see by the energy bucket, when it's 1 meter above the ground, you have actually more kinetic energy than potential energy. When it's halfway down, then it will actually be half and half. It'll be half potential energy and it'll be half kinetic energy. And then as it goes a little bit further, you can see when it's down to 1 meter, which is this right here, you can see there's a little bit more, there's a little bit more kinetic energy than potential energy. And then when it gets down to the bottom, then just before it hits the bottom, of course, then it has only kinetic energy. So effectively, when the h is zero, just before it hits the ground, then it's all kinetic energy, as you can see by the energy bucket right over here. It's all kinetic energy at that point. All right, so when we're problem solving using conservation of mechanical energy, If there is no friction, then the speed of a roller coaster will depend only on its height compared with its starting height. All right, so if we use this as our starting height, which is y above, if we make this our reference point, so this would be 0 down here, and this would be our height h, then the speed of the roller coaster will depend only upon its height above the starting point. And so, or the height above 0, I should say, actually. And so when it's at the top of its height, the speed will be very little, and then as it gets down to its lowest level, that's where its speed will be at the maximum. So up here we're starting with all potential energy, virtually no kinetic energy, and then as the coaster starts down, then at the bottom it will be all kinetic energy, no potential energy, and then this will be somewhere in between. It looks like at this point it'll have a little more potential energy than kinetic energy, but it all depends upon the height above 0. In other words, the h, or the height, which determines the potential energy and hence the kinetic energy. So other forms of energy, energy transformation and the conservation of energy. Some other forms of energy are electric energy, nuclear energy, thermal energy, and chemical energy. And work is done when energy is transferred from one object to another. So accounting for all forms of energy, we find that the total energy neither increases nor decreases. So energy as a whole is conserved. And so we may not always be able to detect all of the different energies that are given off in all forms of motion. However, we can be certain that all of the energy is indeed conserved. So when we're solving problems then, we need to use a number of steps and ask ourselves some questions. So if there is a non-conservative force, such as friction, where do the kinetic and potential energies go? Well, they become heat. So when you're dealing with a problem that does have friction, then that friction is just dissipated as heat. And so once again, you may not be able to detect all of that heat. However, if you have instruments, let me go back. If you have instruments that are sensitive enough, you will be able to see changes in temperature with the objects that are involved with that transfer of heat energy. And so we can't always measure all of it, but you can actually see some difference in temperature because some of that energy has to be dissipated as heat. And so this would be the non-conserving force, for example, friction. So when solving problems then, there's a number of steps that you want to go through. And once again, draw a diagram, okay? That's just the way it goes. You always want to draw a picture so that when you draw a picture, you recognize that you fully understand the situation, and you have all your forces on there, you have the direction of motion on there, you have the acceleration, all of those things to help you solve the problem. The diagram, once again, is the critical piece in order to solve these kinds of problems. So determine the system for which energy will be conserved, and then figure out what you are looking for and decide on the initial and the final positions. All right, so look at, okay, where's my initial position and where's my final position for the particular object in question. So choose a logical reference frame. In other words, determine your origin, where the object is starting from, and those sorts of things. Then apply the conservation of energy, and then that'll allow you to solve the problem. And having said that, I just want to end with this here, and that is the work energy equation. And this is the form of it that we will be working with mostly. And it looks like this. So the energy initial of the system, plus any non-conserving work that's done to the system, whether it's friction or an applied force, that has to equal the final energy of the system. So if there are no non-conserving forces at play, then it's just simply the energy initial equals the energy final. However, with that, what you need to do is make sure that you include, look at both the potential energy and the kinetic energy from your starting point. Because an object may have one or the other or both. An object may start with potential energy or kinetic energy, or it might start with both potential energy and kinetic energy. Then determine whether you have a non-conserving force, like friction or an applied force. And if so, then that has to be accounted for as well. And then, all of this together will have to equal the final energy. And once again, the object may have either just potential energy, or it might have just kinetic energy, or it might have both potential energy and kinetic energy. And so you need to know what types of energies that you're dealing with. So the non-conserving forces then would be friction or an applied force. Those are pretty much the, I don't think we look at many more than that, actually, the non-conserving forces. And so when you look at gravity, gravity is already accounted for with the potential energy in the form of mgh. And so that's why we call gravity a conserving force. It's already built into the work-energy equation, so we don't have to worry about it. The only thing you have to worry about is if there is a non-conserving force, such as friction or an applied force. And so we need to use, basically we use that form of the equation with solving problems, and use the steps that were listed in the previous frames, and then that will help you with a lot of confidence and success in dealing with these kinds of problems.